So let me share you the presentation screen. Hope I think the presentation screen is visible to all of you. Is it visible?
Yes, sir.
Confirm on this whiteboard. That means the whiteboard. Is it visible to you?
Yes, sir.
Okay. Okay. So just I want you to make a note of a problem before we try to solve this problem in Ansys environment. So make a note of a problem. Consider consider a cantilever beam. Consider a cantilever beam. Consider a cantilever beam. Consider a cantilever beam whose one end is fixed. Whose one end is fixed. Whose one end is fixed, and the other end is applied with a load of and the other end is applied with a load of and the other end is applied with a load of and the other end is applied with a load of 10,000 Newton with a load of 10,000 Newton with a load of 10,000 Newton. Full stop. Assume the beam has a square cross section of assume the beam has a square cross section of assume the beam has a solid square cross section. We can incorporate term solid there. Solid square cross section. Solid square cross section. Solid square cross section of dimension 200 mm by 200 mm 200 mm by 200 mm 200 mm by 200 mm and a length of 1000 millimeter and a length of 1000 millimeter and a length of 1000 millimeter. Full stop. Assume the beam is made up of mild steel. Assume the beam is made up of mild steel. Assume the beam is made up of mild steel with a Young's modulus value of with a Young's modulus value of with a Young's modulus value of 200 200 200 200 into 200 into 10 power 3 200 into 10 power 3 Newton per millimeter square. Newton per millimeter square. Newton per millimeter square. Full stop. Extract 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 the deflection extract the deflection extract the deflection shear force comma bending moment diagram, extract the deflection, comma shear force, comma bending moment diagram, and the solution reaction solution through ANSYS environment. Through ANSYS environment. Through ANSYS environment. Hope I think you would have copied this in your worksheet. I believe that. Okay, so look at this diagram. So this is how exactly when you go through this problem. Okay, sometimes the diagram will not be provided, so you have to go through the problem definition and you have to draw the diagram. So you need to show the free body diagram. Sometimes the diagrams along with the problem definition will also be provided. So this is the possibilities. So but you must be in position to resolve any kind of problem, either it may be without diagram or with diagram, so whatever. So in this case you can notice that he has mentioned that the cantilever beam here whose one end is fixed, one end of this cantilever beam is fixed, the other end is applied with a load of F, that is 10,000 Newton. So which is of 10,000 Newton. So I will just write down here, which is of 10,000 Newton. So 10,000 Newton of load is adding at the free end. So and he has also specified that this cantilever beam has a cross section of 200 by 200 mm. He has also provided these details. It is having a solid square cross section of 200 by 200 mm. I'll just write this 200 by 200 mm, and it is solid in cross section. And he is also specified that the length of this respective cantilever beam, it is of 1000 millimeter. It is of 1000 millimeter. And he has also specified that the cantilever beam is made up of certain material, that is mild steel, and mild steel is configured by its Young's modulus value. So the Young's modulus value is given as E is equal to 200 into 10 power 3 Newton per millimeter square. We should make out of all these details before we try to analyze this kind of problem. So with the help of these parameters, available parameters, we need to extract the unknown result. That means we need to extract the deflection, to what extent the beam can deflect with respect to this force applied at the free end. And we should also indicate or show the shear force and bending moment diagram. Along with that, the reaction force should be indicated, it should be listed out. So that is through the Ansys, that is through the Ansys software environment. So shall we go with the Ansys environment?
Yes,
Shall
sir.
we go? Okay, fine. Meanwhile, while I'm explaining, anywhere else, if you find any doubt, okay, if you are left with any doubt, you can interact with me, and I'm here to help you out. I'll clarify your doubt. Okay, let me share you. Now let me open the Ansys environment. If anybody is have using the Ansys software along with me simultaneously, you can make use of that software so that it will make you to get exposed to the tools. Okay, so after we open the Ansys environment, the first option is you should go to plot controls, style, colors, reverse video. Okay, now here the type of analysis which we are going to perform on beam is structural analysis. It is a structure, hence we need to perform a structural analysis. For that we need to select the preferences. Okay, in the preferences select structural, click OK. Then let's move on to preprocessor, that is the first module. So now let us select an element type. Go to element type, add, and again add. So click on beam. Just click on beam to node 188 as a sub element. Beam as a main element and to node 188 as a sub element. Click OK. Next go to next go to material properties, material models, structural, linear, elastic, isotropic. So now we need to define the Young's modulus value of that beam, which is made up of specific material. So what is the Young's modulus value which we have defined there?
200 e power
202.
3.
So okay, 200 e power 3, 200 e power 3. So leave Poisson's ratio blank. Click OK. Now close this. Now go to sections, beam, common sections. Now here you can type this as name as cantilever beam. Cantilever beam. Name as cantilever beam and subtype, that is solid. Here we have to select the solid and offset to centroid, and let us define the breadth and height of that respective beam. What is the breadth of it? What is the breadth of it? It is of 200. What is the height of it? It is 200. Just click preview and you can have a look at this, how the cross section appears with respect to centroid. Then click OK. Now go to modeling, create key points, inactive coordinate system, define the key point number as 1. Okay, so the key point number 1. So before that, just I would like to clarify here. When I just transform this into line diagram, okay, when I just transform this into line diagram like this, I'm going to transform, consider this as a line diagram. So how many points does it require? Could you please confirm on this? How many points it requires to define the cantilever beam of this type? How many key points does it require?
2, sir.
Okay, so the first key point is located here. The second key point is located here. So this is first key point. This is second key point. Only two key points are required to configure or to build this model. So now open the Ansys environment. Go to key points inactive coordinate system. Enter the key point number as 1. Click apply, or click apply. Automatically it will consider it as 0. The key point number 1 coordinates will be assigned as a 0. Click apply. Next, change this key point number as 2. So now define the distance of the key point number 2. So along x direction. So the key point number 2 is located at a distance of 1000 millimeter along the x direction. Just click OK. So two key points has been defined here. Now with respect to these two key points, we need to define or connect a line. So go to lines, create lines, line, straight line. Just select the first key point and the second key point. So the line will be created. Okay. Next, go to meshing, size controls, manual size, lines, picked lines. Picked lines. Click on the line, select that line, then click OK. Now we can divide that into number of element divisions as 50. I'll divide it into 50 number of divisions. The 1000 mm whatever we have, right, 1000 mm line, that will be divided into 50 number of sub elements, segments. So click OK. Once after that, you just go to mesh here, mesh option, click on lines, just click on pick all. So it has been meshed successfully. It has been meshed successfully. Now go to solution, define loads, apply structural displacement on key points. Displacement on key points. You can notice that the first key point is arrested in all directions. That means here first key point has to be defined with all degrees of freedom in all directions. It has been arrested. Whereas the second key point is applied with a load of 10,000 Newton in downward direction. Now you can select that key point which has to be constrained. That is key point number 1. Click OK. Now select all degrees of freedom. Click OK. Now go to force or moment. Click on key points. Select the key point number 2. Click OK. Select the direction of force as Fy and define the magnitude of the force as minus 10,000 in a vertically downward direction. Click OK. Now go to solve current load step. Click OK. Close it. Close this. So your solution is done without any error. So next, go to general post processor, plot results, contour plot, nodal solution, degree of freedom solution, y component of displacement. Okay, y component of displacement. Click OK. So you can notice that it will indicate the deformation of the beam with the color code. So where red color indicates the maximum deformation, and the blue color indicates it is the minimum deformation. So from this we can notice that okay, maximum deformation is okay occurring at this region. And we can also, if you want to show the three-dimensional shape of this beam, that can be shown only with this result only. That means with respect to this nodal solution and y component of displacement, with respect to this plot only, we can show the three-dimensional shape of it. For that, you just go to plot controls, style, size and shape, click on display of element on. Just it will be under off condition. Okay, just switch on this display of element on, and you change the real constant multiplier as 1. You define some scale here for this. So click OK. So you can notice here. When I just click on isometric view or oblique view, just this is how it looks like when we just view it from this side. This is how the beam actually appears. And if you want, you can also go to plot controls, animate, deformed results, degree of freedom solution, y component of deformation, and you can increase the time delay, or you can also increase number of frames as 20, time delay as 1 second. So click OK. So you can just have a look at it, how it deforms in a slow. That means its time frame has been increased here. So how the distribution of the stresses takes place, distribution of the strain takes place inside the material, that can be noticed with respect to this. Is that clear? Is that clear, students?
Yes, sir.
Okay. Okay, now you can stop the animation and let's go to the element table, define table, add by sequence, click on SMISE and define the code as 3, SMISE 3, click apply, then again by sequence, SMISE 6, 3, 6, 6, apply, then again by sequence SMISE 16, click apply, again by sequence SMISE 19, let's click OK, close it. Now go to plot results, contour plot, line element result. Now select SMIC 3 at node I, SMIC 16 at node J. Click OK. So just click on front view. So this is how your bending moment looks like, actual bending moment of the cantilever beam, which is subjected to one kind of point load. So next, let's click on line element result. Select SMIC 6 and SMIC 19. Click OK. This is the shear force diagram of this. And if you want to show this reaction solution, go to list results, reaction solution, click on all items, click OK. So you can notice that FY, there is a reaction solution. So Fy will be acting in downward direction, right? Actual Fy. So this is a reaction Fy which is acting in positive, which indicates with positive value. Hope I think I made you understood and I have clarified with this simple problem. Is that clear?
Yes, sir.
Okay. Any doubts? Let me know if you have any doubts before we proceed with the next kind of problem. We need to get clarified here itself, because sometimes what happens right here, in some cases, the cantilever beam, it may also be subjected to the point load like this. It is represented like this, or there is sorry, it may be subjected to the uniformly distributed load like this. Uniformly distributed load all over or up to certain length, it may be subjected to the uniformly distributed load. The uniformly distributed load, it can also be represented in this fashion also, like this. Like this, it can be represented. Sometimes it may also be subjected to the uniformly distributed load like this up to certain extent, and somewhere here it may be subjected to the point load like this. Point load, and again after a certain distance from here, from this point, it may be subjected to the uniformly varying load. This kind of combination of loads can also be noticed on the beams. It is not only on the cantilever beam, it can also be noticed in other kinds of beams with other supports, other kind of combinations of supports. Hope I think, is that clear? Is it clarified?
Yes, sir.
Okay. So please let me know if you have any doubts. If you don't have any doubts, so that we can proceed with the next step. Shall we? Shall we proceed with the next one?
Yes, sir.
Okay. Okay, now have a look at this. I'll just enlarge this diagram. Okay, so now here you can notice that this is an I cross section beam, I cross section beam. So you can notice that this beam is subjected to uniformly distributed load throughout the length. Okay, it is made up of cast alloy steel, cast alloy steel. Okay, that means steel means we can consider the Young's modulus as that of the previous model. So whereas all the parameters like dimensions, they are being mentioned in terms of inches here. We need to convert this into millimeters. Okay, we can convert this into millimeters, and we should find out the same results. We should extract the same results as that of the previous model. So what shall we do here? Okay, now let's convert this respective dimensions into millimeters. So I'll just provide you 30 seconds time meanwhile, so that if you have any doubts, you please let me know, and then we can proceed with the next problem. Meanwhile, I just want you people to convert these dimensions, okay, convert these dimensions into millimeters. Please convert this and let me know in terms of millimeters. So 1 inch is equal to 25.4 millimeters. Is that right?
6.35.
So 254 millimeters is the length. The length of this is 254 millimeters. And let us convert this cross section dimensions into millimeters. So zero point 0.5.
6.35.
Okay, 0.5 into 25.4. Sorry, 0.5 inch, right? 0.5 inch. So, okay, 25.4 divided by 2. Divided by, so 12.7 mm. This is 12.7 mm. Is that right? Okay, this is 25.4. Arshadit,
Sir,
Sai Kiran, see, just clarify on this. So it is 25.4 mm. And this is, again, we
6.3.
are going to divide this. 6.35, right?
Yes, sir.
Okay, 6.35. Fine. No, this is 6.35 mm. Okay, now what about this one? What about this? This has to be transformed into Newton per meter, Newton per millimeter. Newton per millimeter. How to convert LB means, you know what you mean by LB? Pounds. It is pound. So 1 pound is equal to, okay, 1 LB pound is equal to 0.45 kg. 0.45 kg. So 0.45 into 9.81. 81 is equal to
4.410.
into 9.81. 4.14. Okay, 4.14 Newton. Okay, fine. So 10 into 4.14, 10 into 4.14, 10 into 4.14, let me know. 10 into 4.14 is divided by 25.4, 1.629 Newton per millimeter. So this is 1.629 Newton per millimeter. Is that right? Is that right?
Sir, it's 4.41, sir.
4 point?
41, sir.
Oh, 4.41. Okay, wait. 4.41. 4.41. Yes, 4.414 into 10 divided by 25.4. 1.737. 1.737. This is Newton per millimeter. Is that clear? Is that clear? So now what we have to do? In this case, we have to apply this uniformly distributed load. Whatever we come across here, uniformly distributed load. This uniformly distributed load has to be applied in terms of pressure in Ansys. It has to be applied in terms of pressure. That I will tell you how to apply it. How to apply on it. Okay, now let's open the Ansys software. Go to File, Clear, and Start New. Similarly, go to Preferences, Structural, click OK. Preprocessor, element type, add, then again add, beam, to node 188, same procedure. You can follow the same thing as you followed in the previous model. Go to material properties, material models, structural, linear, elastic, isotropic. Define the X modulus value as 200 E3. Click OK. Go to sections, beam, common sections. Now click on cantilever. Just type it as cantilever UDL. Cantilever UDL. And select the cross section as T cross section. So T or I it is. I get a bit confused with it. I, sorry. It is an I cross section. You just click on common sections. Here we find I cross section. Okay, I cross section. From this we can notice that. So here W1, define W1. W1 means this dimension. This is W1. This is W1 and W1. This is W2, W3. This is W2. This is W3. And then This is T1, T2, T3. Okay, this is T1, T2, and this is T3. T3. So let's define now, but we doesn't know T3. But how to calculate T3? Do you have T3 here? Okay, W1 and W2 they are same, right? One and same. W1 and W2 is same, and T3 is 12.7 mm. Okay, fine. W1, just click on that. W1 is how much? You need to help me out because often and often I cannot just click on the screen and I cannot come back. You people have to help me out. It should be like a two-sided discussion. So W1 is 25.4. W1 and W2 is 25.4 as well as W3. So 25.4. This is 25.4. This
W2 will be 0.5 now, sir.
0.4. What?
Sir, W2 is
No,
0.5
no.
inch.
Here it is this one T3. 0.5 is related to T3. This
Okay,
cross
okay,
section.
okay, sir.
W2 is no. You notice
Ah,
here.
no, got it. Okay, okay.
Okay.
Ah, sir.
So W2 and W1 they are one and the same. W1 and W2 is same. Okay.
Okay,
Fine.
sir.
Now T1 and T2. T1 is 6.35, T2 is 6.35, and T3 is 12.7. Okay. T1 is 6.35, T2 is 6.35, T3 is 12.7. Fine. Now click on preview. So hope I think we have created a model, cross section of it. Just click OK. Now go to modeling, create key points, inactive coordinate system. Okay, now before that I just would like to clarify. So how many key points does it require? Could you please clarify on this in order to create a model, create this model? How many key points it requires? How many key points? This is how the line diagram looks like. So it requires the key point number 1 here, key point number 2 here. So with the help of these key points 1 and 2, we can create a beam. Fine. Okay, click enter the key point number as 1. Okay, click apply. Key point number, change the key point number as 2. Okay, distance of the key point number 2 is 254. It is located at a distance of 254. Click OK. Then go to create lines, straight line, click Select key point number 1 and 2. Finish it. So model, that is the line has been created. Model has been created. Now go to meshing, size controls, manual size, lines, picket lines. Select the line, click OK. Set the number of divisions as 50. Click OK. Now go to mesh lines. Just click pick all. Now go to solution, define loads, apply structural displacement on key points. Select key point number 1. So this key point number 1 is constrained in all directions. Click OK. Select all degrees of freedom. Then click OK. Now go to force or moment on key points. So not force or moment, sorry. Now here we need to change. So that is pressure on lines. We should select the pressure on lines or pressure on beams. Click on pressure on beams. Sorry, pressure on beams. Now what I'll do, I'll just click on box option here, box. After clicking on apply pressure on beams, I'll select box type here, box type, and click OK. Just hold on, box. Then after selecting the box, you just use the cursor, that is pointer here, and you just drag it up to the last. So all the elements will be selected here. Since the load is distributed uniformly throughout its length, we need to select all the elements here. If, for example, by chance, the load, uniformly distributed load was applied up to like 50 mm distance, so then you should select up to that distance only. That is that part only. You should select that part only, that part of elements, and you should apply that UDL on it. Okay, now since the uniformly distributed load is acting all over the length of the body, so click OK. Now it will ask you to define that load parameter. So the pressure value at node I, the value of here load key option is there. If you find a load key option here, change this load key as 2. It's a load key factor 2, which is mainly used for UDL, uniformly distributed load. Now define the pressure at node I, so which is of 1.737, 1.737, 1.737, and pressure value at node J, which is uniform 1.737. So now click OK. So you can notice that how the uniformly distributed load is applied on the beam throughout its length. Hope, is that clear? Now go to solve current load step, click on OK. Solution is done without any error. Close it. Go to general post processor. Now go to plot results, contour plot, nodal solution. degree of freedom solution, y component of displacement, click OK. So it implies what is the maximum amount of displacement it is induced with. Now go to element table, define table, add by sequence SMIC 3, click apply, by sequence SMIC 6, apply, by sequence SMIC 16, apply, by sequence SMIC 19, click OK, close it. Now go to plot results, contour plot, line element result, select SMIC 3 and SMIC 16, click OK. So this is how the bending moment diagram appears. Click on alignment result, click on 6 and 19. So this is the shell force diagram. So for that, go to nodal solution, y component of displacement, click OK, and we'll see how it may appear or look like. Go to style, size and shape, click on 1, change this as 1. So can you notice it? The cross section of it? That's all. So you need to extract these results, required results. Nothing else to be performed. I'll clear this. See, this is another kind of cantilever beam. So where you can notice that. So where up to certain distance, the uniformly distributed load is applied here, and also it is also subjected to the point load over it. Sometimes it may also be induced with a moment, bending moment. So moment value will also be provided. So we can also apply all these required parameters. So here, see, if you or if from this we can just have a glance. So here, when we convert this into line diagram, when I just convert this into line diagram, okay, this is how it looks like in the Ansys environment. So here you can notice that total length of this beam is, the total length of this beam is 1.8 plus 1.2. That means 3 meters. 3 meters means 3000 millimeters. 3000 millimeters. And here it is all from this we can also notice that this load 30 kilonewton per meter, whatever it is been mentioned, right, it is distributed up to 1800 millimeters. This is distributed up to 1800 millimeters. And this load, whatever we come across, uniformly distributed load, okay, it is 30 Newton per millimeter. So I am transferring this K to denominator. So it will become Newton per millimeter. Next, a load is applied here, a point load 50 kilonewton, and another point load is applied at the end. So could you please tell me how many key points does it require? How many key points does it require? How many key points it may require? How many key points it may require? ಏನ್ ನಿದ್ದೆ ಮಾಡ್ಬಿಟ್ಟಿದ್ರಿ ಅನ್ರೋ?
4 sir.
4
ಅಂದ್ರೆ
4
ಇದ್ರಲ್ಲಿ
key points
x1 ಫೈಂಡ್ ಔಟ್ ಮಾಡ್ಬೇಕಲ್ಲ ಸರ್?
ಅಲ್ಲಿ ಎಕ್ಸ್ ನಾನು ಅದ್ರ ಬಗ್ಗೆ ಮಾತಾಡಿಲ್ಲ. ನಾನು ಎಕ್ಸ್ ಅದು ಬೇಡವೇ ಬೇಡ, ಅಲ್ಲಿ ಬಿಟ್ಬಿಟ್ಟಿದೀನಿ.
ಹಂಗಿದ್ರೆ 3 ಸರ್.
ಎಕ್ಸ್ ನನಗೆ ಎಕ್ಸೇ ಬೇಡ, ಇಲ್ಲಿ ಈಗ ಬೇಡವೇ ಬೇಡ ಇದು.
3 ಸರ್.
ಹಂಗಿದ್ರೆ 3 ಎಲ್ಲೆಲ್ಲಿ?
ಎ ಪಾಯಿಂಟ್ ಸರ್, ಆಮೇಲೆ 50 ಕಿಲೋ ನ್ಯೂಟನ್.
ಎಲ್ಲಿಂದ ಎಲ್ಲಿಗೆ? ಫಸ್ಟ್ ಪಾಯಿಂಟ್ ಎಲ್ಲಿ ಸ್ಟಾರ್ಟ್ ಆಗುತ್ತೆ? ಫಸ್ಟ್ ಕೀ ಪಾಯಿಂಟ್ ಎಲ್ಲಿ? ಇಲ್ಲ.
ಹಾ ಸರ್.
ಫಸ್ಟ್ ಕೀ ಪಾಯಿಂಟ್ ಓಕೆ, ಫಿಕ್ಸ್ಡ್ ಪಾಯಿಂಟ್ ಓಕೆ. ಸೆಕೆಂಡ್ ಕೀ ಪಾಯಿಂಟ್ ಎಲ್ಲಿ? ಅಟ್ ಎ ಡಿಸ್ಟೆನ್ಸ್ ಎಷ್ಟು ಡಿಸ್ಟೆನ್ಸ್ ಅಲ್ಲಿ?
1800 ಸರ್ ಮಿಲಿಮೀಟರ್.
ಅಟ್ ವಾಟ್ ಡಿಸ್ಟೆನ್ಸ್? ಓಕೆ, ಇಲ್ಲಿ
1800 mm.
ಆಯ್ತು. ಓಕೆ, ನೆಕ್ಸ್ಟ್
ಆಮೇಲೆ 3000 mm ಸರ್.
So at a distance of 3000 mm from the origin. So now when you just connect this, right, when you connect this from point 1 to point, okay, you need to create one element. Next again from point 2 to 3, you need to create another element. You need to create another element. So that means here we have to create two elements here. So here the first element is subjected to the uniformly distributed load as well as the point load at this point 2, and at point 3 point load. So that means we need to create this model with the help of 3 key points. Okay, and we need to constrain it at point 1, which is fixed, and we need to apply the load on it, specific load mentioned on it. Okay, let me take you through the Ansys software here. I'll start working on it. Go to element type. Let us assume, okay, the beam 2 node 188. Same ಅದನ್ನೇ ನಾನು select ಮಾಡ್ತೀನಿ. Material properties, material models, structural, linear, elastic, isotropic, Young's modulus 2E5. 2E5 ಅಂತ ತಗೋತೀನಿ. Is it sections, beam, common sections? Okay, it's a solid. I'll select 200 as breadth and height as 300. Preview. Click on preview. Okay. Now go to modeling, create key points. Inactive coordinate system. Create the key point number as 1, and key point number 1 is origin point. Click apply. Key point number 2, which is at a distance of 1800. Click apply. And key point number 3, which is at a distance of 3000. Click OK. Then go to lines, straight line. Click 1 to 2, 2 to 3. Click OK. Go to meshing, size controls, manual size, lines, picket lines. Select the first line. Click OK. Number of element divisions are 50. Click apply. Apply the second element. Click OK. Let the number of element divisions be 30. Click OK. Now go to mesh lines. Just click pick all. Now go to solution, define loads, apply structural displacement on key points. Select the key point number 1, select all degrees of freedom, click OK. Then go to force or moment on key points. Select the key point number 2. Okay, here I am going to type this as key point number 2 because it's a bit difficult to select here because it has been divided into different number of segments. So it's a bit difficult to identify which is the key point number 2 sometimes. So otherwise, if it is if we are able to identify it directly, we can select key point number 2. Click OK. Now select the direction of force as Fy and apply the load as 50 kilonewton minus 50,000. Click apply. Then again select the key point number 3. Click OK. And input the value as 40,000 minus 40,000. Click OK. Now go to pressure on beams. Pressure on beams. Select box and select from this point to this point. You should see that sometimes this point, whatever the box you would have dragged, it would have dragged beyond this also, beyond the point 2 also. So for that you have to zoom. Use a zoom option here. We have a zoom option. Just hold on. Something went wrong. Sorry, wait. I'll start doing again. See, if you want to just identify the line numbers and key points, go to plot. Just to click on just on plot controls, numbering, plot controls numbering. Just click on key points on and line numbers on. Just click OK and go to plot, replot. Sorry, plot lines, plot. Automatically, you can notice that. So line number 1 and line number 2, key point numbers, everything will be appearing. Can be easily noticed. So go to solution. Okay, so oh, okay, students, I think I have some problem with my laptop as well as the software. So would you like me to teach that part? Do you want me to teach that part? Yes. Do you want me to teach that part? Sai Kiran?
So my data got over by 3, sir. So I could only hear you, sir. Your PPT is
Okay.
not visible for me, sir.
Sachin, what about you?
Sir. Sir.
So do you want me to just teach it once again?
ಲಾಸ್ಟ್ ಅದು ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡಿಬಿಡಿ ಸರ್ 2 ಪಾಯಿಂಟ್ಸ್ ಹೆಂಗ್ ಇದಾಗುತ್ತಲ್ಲ ಸರ್ ಅದು.
So nothing. What you have to do, you have to drag a box, okay, and you just click on okay. Then automatically you need to apply that value. You have to define those values for uniformly distributed load. At node A and node 3, you define it as 30. Got it? So automatically it will be applied as a uniformly distributed load on it, and then go to solve. So solve it. Okay, if the solution is done, so then it indicates it doesn't have any error. So next you can go with the other parts like results, showing the result. That's it, nothing else, as that of the previous problems. Only during the point of load, application of load only, there you need to apply the load as well as the uh, boundary condition in a uh, what I say is specific way. So I want you people to try some more problems related to cantilever beam. Okay, so next class I will come up with the beams with very different loads. So where the beam will be subjected to point load, as well as it is subjected to UDL, it is subjected to uniformly varying load, and as well as with the moment, with a bending moment. It is subjected to the moment as well as all the loads, all kinds of loads, so that you can easily understand how to analyze any kind of beam. Gautam, is that clear?
Yes, sir.
ಏನೋ ಬರೀ ಎಸ್ ಆರ್ ಅಂತ ಬರ್ತೀಯ ನೀನು, ಇನ್ವಾಲ್ವ್ ಆಗಲ್ವಲ್ಲಪ್ಪ ನೀನು. ಬರೀ ಗುಡ್ ಆಫ್ಟರ್ನೂನ್ ಅಂತೀಯ, ಮಾರ್ನಿಂಗ್ ಅಂತೀಯ ಅಷ್ಟೇ. ಮಧ್ಯದಲ್ಲಿ ಏನು ಡೌಟ್ಸ್ ಇಲ್ವಾ? ಡೌಟ್ಸ್ ಏನ್ ಬರಲ್ವಾ ನಿನ್ಗೆ?
ಇಲ್ಲ ಸರ್, ಡೌಟ್ಸ್ ಇಲ್ಲ ಸರ್.
ಅರ್ಥ ಆಗ್ತಿದ್ಯಾ ನಾನು ಹೇಳ್ಕೊಡೋದು?
ಹೌದು ಸರ್, ಅರ್ಥ ಆಗ್ತಿದೆ.
Okay, you keep solving some other problems, keep trying trying to solve the other problems. You go through some Google, you search in Google, you may get different number of problems on cantilever beam. And whatever the problems I have solved in the previous class also, such a type of problems also you can go through and practice it. So because only if you practice it thoroughly, then only it makes you perfect. Simply being as an silent listeners, it will not help you out. So if you want to be an active uh, if you want to understand the concept thoroughly, you have to practice it. You have to practice it. Okay, I think I will end up this class here itself because the strength is very less. I cannot take this forward. So meanwhile, if any other day, if you need a class, you just let me know that, so that I can also go through whether if I am leisure or not on that particular day or on that particular session, and I can handle it accordingly. So because I just wanted to complete this as early as possible. I don't want to keep this lab as pending, because we doesn't know when the class will start, when the offline class will start, and when the college will start. It is no sign of it. Okay, I'll end up this class here itself. Okay, you may all leave now. Right. Thank you. Keep practicing.